Hello everyone, this is N Poornima Deepthi working as an assistant professor in the Department of ECE at MLR Institute of Technology. So today I will explain how to write a program in 8086 microprocessor. This video is a part of series microprocessors and microcontrollers. Coming to the today's concept, here I will explain two main programs in arithmetical operations using various addressing modes like immediate addressing mode, how we can write program using direct addressing mode, register addressing mode, register indirect addressing mode, and the programs which is involving bit manipulations, how to manipulate bits to write a program. So using this bit manipulation series, I'll explain how to find out whether the given number is a positive or negative number, or the given number is a even or odd numbers, or how many number of ones present in the given number and how many number of zeros present in the given number. So coming to the first program, here the program is using to perform 16-bit arithmetical operations. Arithmetical operations means addition, subtraction, division or multiplication. So how to perform these arithmetical operations while using 8086 microprocessor. But here I'll explain everything by using each and every addressing modes present in 8086 microprocessor. Coming to the immediate addressing mode, as I already told you in the addressing modes concept, that immediate addressing mode means the instruction which is having the immediate or raw data present in that particular instruction. If an instruction is consist of a immediate data or raw data, then we can say that particular instruction is said to be the immediate addressing mode. Here, coming to the programming, here I'm using two segments here. One is data segment and another one is code segment. As I already told you, the memory of 8086 processor has been segmented into different segments. Each segment is of 64 KB. Out of 1 MB memory, it can have 16 segments, or each having 64 KB. Out of that 16 segments, we will use only 4 segments at a time. But out of that 4 segments in this particular program, it is necessary to have only 2 segments. So that's why I'm using data segment and code segment. So here I was initializing the data segment and data ends. So if anything we need to store in the memory, you can directly initialize that particular data in this data segment. Here I've been using only immediate addressing mode. That's why I'm directly giving the data in the instructions itself. That's why I'm not declaring any variables or any data in this particular data segments. So assume is a directive which is used to ease the programmers. So here CS I've been using as a code segment, DS data. So now I'm starting the code. Here these two instructions are used to initialize the data segment within the code segment. So now I can access the data, whatever data present in this particular data segment, I can be use that particular data in this code segment. So now coming to this equation, here the 1, 2, 3, 4 H. So that is the hexadecimal representation of a number of 16-bit data. So this particular number I have directly mentioned in the instruction itself. So that's why these two particular instructions are said to be the immediate addressing mode. So here the AX register is a 16-bit register which is filled with the number 1, 2, 3, 4 hexadecimal number. And here the BX register is also a 16-bit register which the number is 4, 5, 6, 7 H. So here I was moving, you can directly move data into the registers, or you can directly access the second data in that particular add instruction itself. Here the add, so we need to add two 16-bit numbers. The number present in AX register, the AX register is having 1, 2, 3, 4 H number, and the number itself directly mentioned in the add instruction itself. So this particular instruction also comes under the immediate addressing mode. So now the value present in the AX register will be added to the value 4, 5, 67H directly. 4567H directly. So the output, as you all know, that the output will always be stored in the destination register itself. Here the destination register is AX. So after performing the addition operation, the output is available at the AX register itself. So what is the output at present at AX register? Here 7 plus 4, which is nothing but 11. The representation of 11 in hexadecimal series is big. So while adding 6 plus 3, you will get 9. Here you will get 7. So the output which is present at AX register is 579BH. This is the output present at AX register. So if we are performing subtraction, so you can write subtraction. So subtract BX register, comma 4567. So the value present in BX register will be subtracted with the direct value. So you will get answer 0. And here in this particular instruction, the output will be present in which register? So as I already said that the output will always present in the destination register. In this particular instruction, the destination register is a BX register. So what is the value present in BX register? This is the value 000H is the value which is present in BX register. Apart from this, you can directly write multiplication also. So multiply 4567H or divide 12H. Like that, you can directly mention the data itself in the. So here in this particular register, I didn't mention the destination register. Why? So in these two cases, multiplication and division in 8086, the destination register will always be the register AX. That's why I have didn't mention any AX register, destination register in this particular two instructions. So multiplication instruction and division instruction, these two instructions will always have the destination register as AX register. So this is all about the immediate addressing mode. Coming to the next one, here it is a direct addressing mode. So direct addressing mode is nothing but we will mention the address itself in this particular instruction. See here, I'll be initializing, I'll be declaring some variables, like I was storing some data in this particular data segment. Here number 1. So DW is a defined word. So 16-bit data, 16-bit memory will be allocated to store this 1234H. So suppose you will take the data segment register is having the segment value as, like, consider it as 2000H. In this particular register, so I'm just dividing it. The memory will be like the continuous memory only. For both of the memories, the DS will having 2000H. This is the segment value. So now we will have the offset value also. Like consider this offset value as 4 zeros H, 0001H, 0002H, 0003H, and these value as like randomly I was taking like 1001H. Now in this particular number 1 is the label of that particular data 1234. So I have already told in the previous videos that the lower significant byte will be stored in the first memory and then followed by the highest significant byte. So here 34 will be stored in first memory and followed by 12. So here the label will be the number 1. So segment address is different. This will be called as the offset address. So, and this is the label given to this particular number stored in that particular memory location. Here I was storing that number 2 is taking here. 78H will be stored here. So this is how we will initialize the data in that particular data segment. Now I already took result as the variable to store the output after getting the output from the instructions. So a question mark represents it will allocate duplicate memory locations to store. We didn't know how many data, how much bits of output will be available after executing this particular program. So the output can be of 8-bit value, can be of 16-bit value, or can be of 32-bit value. So that's why here I was allocating word byte, question mark represents the duplicate memory locations. It will allocate some memory locations, depends upon the output. So coming to these two instructions are used to initialize the data segment within the code segment. Now coming to the main program, here move AX comma number 1. So number 1, as already we stored the data in this particular memory location. So here number 1 represents the data 1234H. So this will be moved to the AX register. Now AX register is having 1234H data. Now coming to the next instruction, here we are adding the data present in AX register with number 2 value. So number 2 is a label. So what is the number 2 value? So number 2 value is 5678H. So in this particular instruction, we've been directly mentioning the address, like address of this particular segment, particular memory. So this mentioning the address directly in the instruction itself is nothing but the direct addressing mode. So here addition will be performed between the two. One is of the register AX. The value present in the register AX is 1234H, and the number 2 value. Number 2 value is 5678H. So what will be the output after? Here it is a addition operation. So we will perform addition operations. 8 plus 4 is 12. 12 in hexadecimal number can be represented by C. 7 plus 3 is 10. It can be represented by A. 6 plus 2, 8. 5 plus 1, 6. So this will be the output presented, output we will get after executing this instruction. But which register will hold this particular output? As I already mentioned, the destination register will hold this particular value. So AX register is having the value 68ACH. Now it's our time to represent this AX register value to store in another memory segment, which is given by the result. So here this output will be stored like this. So this is how we will write programming using direct addressing mode. Coming to the register addressing mode. In particular register addressing mode, we can know that the particular instruction will have two registers. Source and the code. Source and the destination will always be the registers itself. So here it will be like immediate addressing mode, but this particular instruction will say the register addressing mode. How? Because the destination register is AX and the source register is BX. So the data present in AX register will be added to the data present in the BX register. The AX register is having 1234H and BX register is holding the data 0020H. Now after performing addition operation, we will get the value 1254H. So the data, first destination and the source, two operands will be of the registers itself. So if in particular instruction, if two operands are registers, then you can say that it is a register addressing mode. So when can you say that register indirect addressing mode? If the address of that particular memory is mentioned in the indirect way. So then you can say that it is a register indirect addressing mode. In this particular program, these two I already told you that to initialize the values. So now the offset values of these particular locations will be holded by the index registers, either SI or DI. For particular data segment, we will use this SI and DI registers to hold the offset value. So the offset of value 1. So what is the offset of value 1 here? 0001H. That will be stored in SA register. The offset of the second value 2, like take 1200, for example, stored in DI registers. Now in this particular instruction, I was indirectly mentioning, brackets represents the indirect. So whatever the data present in SI will be the address of that particular memory location. So here SI, what is the value of SI? 0001. So here we are indirectly saying that the data present in the location of 0001H will be fetched and moved to the AX register. See, in this particular example, the data present in value 1 is 3412. Let us take this one as 1000 and this one as 1. The second, this one is the value 1 and this one is the value 2. The data present in this one is 2301H. So let us consider this as 2000 and this as 2001. Now in this particular instruction, what it is saying? So SI is having the offset value of value 1. So value 1, what is the offset value? Starting address 1000. In this particular instruction, it is saying that DI is having the offset value of 2. So the value of offset value is 2000. So in this particular instruction, we are saying that the data present in the address location present in SI. So what is the address present in SI? 1000. So the data present in the 1000 will be moved to the AX register. What is the data? 341. In this one, the data present in the location which is present in the DI register, it is 2000. The data present in 2000 is moved to the BX register 0123. Now you can perform addition. So if we are mentioning the data present in memory indirectly using the registers of any index or pointer registers, then particular instructions, those instructions are said to be register indirect addressing mode. So I thought it was clear coming to the arithmetical operations. Now coming to the next set of programming, which is nothing but bit manipulations. So bit manipulations is the changing of the simple bits. So in this particular program, they are asking to find the data is positive or negative. So how can you say that data is positive or negative? If we are dealing with the decimal numbers, we can directly say that the sign plus indicates the positive numbers and the sign minus indicate the negative numbers. So here we are dealing with the binary numbers. How can you say that the binary number is a positive or negative number? So you can say that the most significant bit, if the most significant bit is equals to 0, in signed operations, if the most significant bit is equals to 0, you can say that that one is a positive number. If the most significant bit is equals to 1, you can say that it is a negative number. So based upon this logic, I have already written the program how to find out a positive or negative number. Let us see. So in this one, I have taken 25. So how can we write a 25 hexadecimal number in the binary number? So number 1 is 25. So we can write 25 in binary as 0101H binary. So this is the number. So we need to find out whether the given number is a positive number or negative number. By simply looking here as the number represents here itself, you can directly say that the most significant bit is a 0. So it is a positive number. While looking here, we can directly say, but how processor will identify whether it is a given, whether it is a positive or negative? So we need to write a logic depending upon the bit manipulations. So you can find out the first most significant number. If the number is 0, you can say it is a positive. If the number is 1, you can say it is a negative. So here I have already taken message 1. So how we can identify whether, so it can see that given number is a positive. So if we are getting the positive number, it will display given number is a positive. So if we are getting a negative number, it will display given number is a negative. That is the logic we need to write here. So here message 1 is positive, message 2 is negative. I have already initialized in the data segment itself. Now coming to these two instructions are used to initialize the data segment within the code segment. Now coming to this, AL register is having the number 250010 and 0101. So now the next instruction is rotate instruction. Rotate left, ROL, rotate left. As I already told you in the instructions video, that rotate instruction is used to shift, and the most significant bit will be the least significant bit, while in the case of LSB. But here the carry bit will be there. So if we are shifting this number left side, so the numbers will be moved like this. It will be moved to the carry bit 0, 0, 1, 0, 0 and 1, 0, 1. Previous carry will be affected here, where if it is 0 or 1, it depends upon the previous carry digit. So now you can check that if the carry is having 0, we can say that it is a positive number. If the carry is having 1, we can say that it is a negative number. So here in this particular case, it is 0. So next instruction is jump if carry. JC represent jump if carry is there. So it will check the carry bit. Is there a 1? No, carry is not there. So it is 0. So it will neglect this particular jump instruction. It will lead to the next instruction. What is the next instruction? LEADX message 1. So here I was loading the LEA means load effective address. Load effective address of this particular message 1 to the register DX. Move AH comma 09H followed by int 21H. These two are the combination of DOS interrupts which is used to display the complete string. Here the complete string will be displayed. If you want to display only one character, the data will be changed here. So these two are instructions to display a string completely. DOS interrupts. So coming to the, it will display. What it will display? Message 1 is nothing but given number is positive. Let us take one example of a number 84H. If we are taking 84H, the number, how we will represent the number 1000 and 0100. Here the most significant bit. While performing the rotate operation, this 1 will be moved to the carry, and yes, while getting the JC instruction, jump if carry, yes, carry is there. Where it needs to jump? So it needs to jump to the label NEG1, negative 1. So it will directly jump to this particular label, and here these two are the these three are the instructions to display the message string. What is the message string here? Message 2, given number is a negative number. So this is how we will find whether the given number is a positive number or negative number. Next, coming to the next program. Yes, here it is to identify whether the given number is a even or odd. So how to identify? So in the case of decimal numbers, we can divide it by 2. The number will be divided by 2. If remainder is there, then you can say that a number is a odd number. If not, remainder is not there, like remainder is 0, you can directly say that the number is even number. In the particular case of decimal numbers, but here it is a binary numbers. How to identify whether the given number is a positive or negative, even or odd in binary numbers? So let us say the binary numbers representation will always be like 2 power 0, like so on. So if this number 2 power 0 means 1. So if a number is divisible by 2, if we are having the remainder as 1, you can say that the number is a odd number. So if it is not there, 2 power 0, so the least significant bit of binary number will decide whether the given number is a even or not. So least significant bit is 0, you can say that it is a even number. If the least significant bit is 1, you can say that it is a odd number. So this is the logic behind this program. This program is also similar to the previous program, but the thing is here we need to check the least significant bit. So how to check the least significant bit? Previous slide I have already told you how to check the most significant bit. If we are rotating the particular number left side, we will get the most significant bit. So here we need to have the least significant bit. So here we can rotate the instruction right side. So that is the difference between the, else the remaining same. So it will rotate. So what is the, here I have taken 2 5. 2 means 0 0 1 0 0 1 0 1. So here rotate right. So the instruction, the data will be rotated right side. Here I have mentioned only one time. So it will rotate to the right side. 1 will go to the carry bit 0 1 0 0 1 0 0. This will be depends upon the previous carry. So here what is the carry? 1. So now we are checking JC. Jump if carry is there. Carry is there? Yes, there is a carry. 1 is present in that carry bit. So the number is a odd number. So it will jump to the odd label. So here odd label represents the message to, what is the message to? Given number is a odd. So the given number is 2 5 is a odd number. Okay. Next, coming to the next program, to identify how many ones and zeros are present in this particular number given. So here I was taking 5 6. 5 means 0 1 0 1. 6 means 0 1 1 0. So while rotating each and every bit, we can identify whether the bit is 0 or 1. So now these two are used to initialize the data segments. Now coming to XOR operation. Why we are performing XOR with AX and again AX register? So there is two instructions to erase the data or to set AX values to 0. How? If I can write move AX comma 0 0 0 0 H to initialize AX register with zeros values. So to empty the register, you can directly mention this instruction. Instead of this instruction, you can write XOR operation between AX and AX. Why? So if we are having the same inputs in the XOR operation, 1 and 1, you will get the output 0. And 0 and 0, you will get the output 0. If we are having different, then only we will get output as 1. But AX means the same data will be XORed with each other. So the output will always be 0 0. So you can use these two instructions to erase that, to initialize AX register with all zeros, to remove the data present in any register, not only AX register. So coming to the, so now AX register will be filled with 0 0 0 0 H. So now SA register will filled with N1. So 56 will be moved to the, so here as I already told you, DX register is 4 zeros. BX register is also resetted. Why? What is the need of using BX and DX register? As I already told you, this program is to identify how many ones, logical ones and logical zeros are present in the given input. So to store these two outputs, we need to have two registers. Here DX and BX register is used to hold the two outputs. That's why I was initializing the registers with all 0 values. Now coming to the CX register. Usually CX register is used to keep the count. Here I was keeping the count as 8. Why I keep 8? Because here I took 8-bit data. So to perform operations, to check each and every bit, I need to have 8 as a CX register count. So if I was taking 1 2 3 4 like 16-bit data, then I need to keep here as a 16. So the data present in SA register. So how? Value is stored in 56. Suppose take it as H. So this is 1. So this value SI is having the offset address. So the data present in this offset address is 56 is moved to AL register. Now AL register is having 0101 0110. As we are giving the data as a hexadecimal number, but the operations performed inside the microprocessor is the binary numbers. That's why I am taking a binary number to explain the concept. So here first one, what? Rotate left side. Left side we was rotating one time. So this one will move to the carry register. Here 0 will be moved to the carry register. So it will check jump if carry X. X is the label. So jump if carry. If carry is there, then it will jump to the X. No, here there is no carry because 0 is present in this particular location. So now CX register is initialized with 8. Here 0. So jump if carry, no, not carry is there, it will move to the next instruction. Next instruction is increment BX. So BX register will be incremented. Initialize previous BX registers are all zeros. So it will incremented by 1. So this is the register which used to hold the number of zeros, and this is the register which is used to hold number of ones present in the instruction itself. So coming to the next one, here BX register will be incremented and it will become 0001. Next, decrement DX register, CX register. Why? Already we have verified first digit. So only 7 digits are remaining. So you need to decrement CX register. CX register will get decremented by 1 and it is the value 7. So it will check if jump if not 0 back. If the CX register is not 0, then only it will get back to the label back. So it will again go to this particular instruction. It will again execute this particular instruction. Now, next. So what is the data present after executing this one? So now this next bit will be rotated. It will get into the carry register. Now jump if carry is there. Yes, we have gotten the carry. So it will executed increment DX register. DX register will get incremented. Like this, how many times we are getting the number of ones, it will be loaded in the DX register and number of zeros will be loaded into the VX register. These are the two outputs we will get after performing this particular program. So until now I have discussed how to write programs in 8086. I have explained the arithmetical operations programs using different addressing modes and how to write bit manipulation programs. Thank you.